Hello, welcome back. In this video, we are going to continue with our assignment problem. So in our first part, we've seen how to solve the assignment problem using the Hungarian method, but our problem was simply minimizing problem. So we wanted to minimize the distance covered by different engineers to cover the various customers. So you can watch that video to refer to that. Now, in this video, we are going to see how to solve a maximization problem, right? The other one was minimization. So this one, we are looking at maximization. So in maximization problem, we're going to change the first step in the Hungarian method by reducing the maximum value in column reduction, all right? The other one, remember, we did what we call column reduction by reducing the minimum value. So in this case, we're going to reduce the maximum value. So in my example I'm giving you now, we have a case where there are various towns, let's say town A, B, C, D, and then we have salesmen W, X, Y, and Z, all right? And these salesmen want to maximize the revenue. So you can see these are the revenues expected to be generated by these salesmen in different towns. So by allocating effectively, we can be able to maximize the revenue. So our problem is find the maximum revenue by assigning the salesmen to the best town they can be able to serve well. So to do that, our first step will be a bit different. So you're going to start by column reduction, all right? Column reduction. But in column reduction, we're going to use the maximum value in each column, all right? So maximum value in each column. So we're going to start the first column here. The maximum value here is 38. So we get our maximum value. So maximum value here is, we have 28. Maximum value here is 53. Maximum value here is, we have 30. So reduce each maximum value, bearing in mind that we ignore negative values. So we take all values to be positive, all right? So I'll have by new matrix A, B, C, D. Then I have the salesmen X, W, X, Y, and Z. So in this scenario now, I'm going to see in a different perspective. This is a maximization problem. So so the first one I'm going to subtract, yeah? So 38 minus 25, so I'm going to record here. So that's what I'm going to do. 38 minus 25, that is the maximum value. So 38 minus 25, that's the largest value. So we use our calculator. That's 38 minus 25. Yes, that gives us 13. So we subtract 38 minus 38, so I have 0. 38 minus 15. 38 minus 15, that gives me 23. 38 minus 26, that gives me 12. So also the second column, so that 28 minus 18, I have 10. So 15 minus, maybe 28 minus 15. 28 minus 15, I'll have 13. 17 minus 28, I have simply 11. Then 28 minus 28, 0. So I have the third column. 23 minus 53 minus 23, I'll have 30. So here I have 0. 53 minus 41, of course, that gives me 12. 53 minus 36, that gives me 17. Then the last one, I have 30 minus 14, that gives me 16. So I have 23 minus 30, that gives me 7. So 0, 30 minus 30, 0. 29 minus 30, 1. So this is my new matrix after performing what we call column reduction. And you've noted that this is different from the other one because what changes here is that we are using the maximum value to perform column reduction. Now the other steps will remain unchanged, like in the first minimization case. So the second step now is to perform row reduction. Row reduction. So I'm going to draw a new matrix. So I have A, B, C, D. So I have W, X, Y, Z. Alright, so this is my new matrix. Now, so in this case, I'm going to identify the minimum value in each row. Minimum value in each row. So remember, I've said all the other steps remain unchanged. Minimum value. Here only we get the maximum. So right, we have minimum value here is 10. Minimum value here is 0. Minimum value here is 0. Minimum value here is 0. Alright, so we can do that. Let's get our final matrix. So I have 13 minus 10, I have 3. I have 0. 10 minus 10 is 0. 30 minus 10, I have 20. 16 minus 10, I have 6. Like that. So all these are 0, so the values are going to remain unchanged. So I have 0, 13, I have 0, 7. So I also have 23, I have 11, I have 12, 0, then the last one, 12. Of course, nothing is changing in these last 3 rows. 0, 17, 1, like that. So what I'm going to do next is perform the same operation. Step number 2, cover with minimum number of lines. Alright. So I'll cover with minimum number of lines. So I'll check. I have 2 zeros here. I have 2 zeros here. So I can cover this. So let me call this one my line 1. This one is my line 2. Okay, line 2. Now I have still 1 0 here remaining. So I cover this. I can decide to cover this way or this way. So I can choose to cover this way. So this is line 3. So what you can see is that the number of lines, m is equals to 3. However, m should be equal to 4. So in this case, m is not equal to 4. So we have not reached optimal solution. This one will take us to go back to step number 4 and perform some operations whereby we're going to, yes, so let's see step number 4. We're going to have a new matrix. So I'll have A, B, C, D. So in my new matrix, I'll have W, X, Y, and Z. So this is what I'm going to do. So in step number 4, we say that you need to identify the minimum uncovered value. So let's check those values which were not covered. So we have 12 here. Yeah, I have 12, I have 17, 1, I have 6, I have 20, I have 3. So I check the values which are not covered. So the minimum value of course is 1. So minimum value x is equals to 1. So we say that in the Hungarian method, the second procedure is to add this value to all the corner points. That means those points covered by 2 lines. Of course, you can see I have these points covered by 2 lines. Then I have this. So I have 13 and 11. 13 and 11 covered by 2 points. So I'll come and write 13 plus 11. 13 plus 1, sorry, that gives me 14. Then I have 11 plus 1, that gives me 12. Now let me bring back all the values covered by 1 line. So I have 0, 0 here, I have 0, alright, 0, 0. This line number 2, it covers 0, 0, 7, 0, 0, 7. I can also see the other line covered here by 1 line. I have 23, 12 and 0. 23, 12 and 0. Now for the values which were not covered, we subtract from the minimum value. So the minimum value of course is 1. So I have 3 minus 1, I'll have 2. So here I have 20 minus 1, I have 19. 6 minus 1, I'll have 5. Alright, this gives me 5. Then 1 minus 1 here, 0. 17 minus 1 give me 16. 12 minus 1 here give me 11. So that's my new matrix. After getting this matrix, after performing step number 4, I go back to step number 2 by covering all zeros with minimum number of lines. So you can see here. So you can see I have 1 0 here, so I have 1 0 here. So I can prioritize to cover 2 zeros. So I have this. So let me cover these zeros. So this is my line 1. Then I cover, there are 2 zeros here again. Alright. So I can decide to cover this way or vertically. So there is another 2 zeros here. So I can cover it like this. So I have this my line 2. There are 2 zeros here. I can cover it with 1 line again. So this is my line 3. So let's see if the number of zeros is covered. How many lines do we have? So I have line 1, I have line 2, and I have line 3. So it means we are yet to reach optimal solution. So you can also say, since m is still equal to 4, and then m is not equal to 4, then basically we repeat the same step number 4. So we're going to repeat the step number 4 again. So I'm going to have another new matrix and perform similar operations. Alright, so I'll have A, B, C, D. Then I have W, X, Y, and Z. Alright, so I want now to perform step number 4 again. So in this step number 4, I want to identify minimum value, minimum uncovered value, right? So minimum value X, which is uncovered. So let's see in this matrix. So we identify the minimum uncovered value. We have 2 here, we have 23, we have 11, we have 19, we have 12 and 16. Alright, so those are the values uncovered. So I can see my minimum value is going to be 2. So X is 2. So let me see now what I will have for X. So in my value of X now, what I will have here, so let's now reduce. So we have, so subtract or add to all corner points. So I have corner point here, I have 14. The other corner point is 14, is one line, then I have this 7. So I'll add, so 14, so I'll have 14 plus 2, I have 16. Then this other one I have 7 plus 2, I'll have 9. Alright, so all the other values which are in the lines will remain unchanged. So I have 0, I have 12, I have 0. Now on this line I have 0, I have 0, of course 7 here is covered. Then I have, of course I have that. Now look at all that line. So I have all the values in the lines. Now let's check all the uncovered values. So the uncovered value is 2, 2 minus 2, 0. 11 minus, so I have 23 minus 2, I have 21. 11 minus 2, I have 9. Then here I have 12 minus 2, 10. 16 minus 2, I have 16 minus 2 basically give me 14. Of course there are values here I was to put 0 and 0. So these ones were covered by a line. Now we do the final, or we do the step number 2 again by covering with the minimum number of lines possible. So let's see how many zeros we have. 0 here. Sorry, there is 19 here. Of course, I have not put that. So there is 5 covered point. Then there is 19. 19 minus 2 is 17. Sorry for that. So we have this. We can cover the first line here. So this is my line 1. All right. Then I can see there are 2 zeros again here. All right. There are 2 zeros. So I can cover the 2 zeros. So this is my line 2. I can see there are 3 zeros. There are 2 zeros here. I can cover them. So this is my line 3. But there is still 0 here which is uncovered. I can cover it vertically. So this is line 4. So in this scenario now, I can say m is equals to 4. That means I have reached optimal solution. This will take me to the last step, stage number 5, where I'm going to do the final allocation. Alright, so let me come up with my final matrix. My final matrix of allocation. So what I'm going to do here, I will assign the salesman to the job. So I have, let's say the towns, then I have salesmen, then I have revenue expectation in dollars. Alright, so what I'm going to do in step 5, we said we use step 5 we said we use row and column scanning. We use row and column scanning in step number 5. Alright, so let's perform row and column scanning here. So we start with the rows, then go to columns. So of course I can check here, there are 2 zeros, there is no unique 0. Here there are 2 zeros, no unique 0. Here there is 1 0 here, so this is a unique 0. So I allocate that one, cancel the 0 on the same column. I go to the last row. Now there is a unique 0, alright? I allocate it. Cancel any 0 in that line, so I cancel this. Now let me perform now column scanning. So I can check. There are 2 zeros here, no unique 0. The second one here, I have no 0, done. Here, I have 1 unique 0, so I have this, I allocate, alright? So I cancel any other 0 on that row. So I go to the last one, of course, we are done with this. So I perform again row scanning. So I can see now the first row, there is a unique 0 here. I will allocate. I check the second row, we are done with it. The third row, we are done with it. The fourth row, we are done with it. So in this case, we have done our full allocation. So I can now come up with my final matrix. So you can see in so we have towns A, B, C, and town D. So in this town, I have allocated W to salesman W. So you can see the initial matrix A to W is giving 25. Now I can see the next one B is allocated to Y. So I can see Y have B to Y, so 53. So that is $53. I can see C is allocated to Z. So I can write Z. So the revenue here, C allocated to Z is $30. Then the final D, I can see D here is allocated to X. So revenue is going to give me for X case. So I can see X is allocated to, sorry, we have X here is allocated to D, yes. So the distance is 28, not distance but revenue. So we do the addition of that, that will give us total revenue that we expect from all our sales agent sent at different locations. So I'm going to see now, that's 25 plus 53 plus 30 plus 28. So that gives me $136, alright? So that is the expected revenue by using the maximization. So that's how we solve a problem of assignment using maximization until we find our final allocation here. Thank you so much. See you in our next video.